See, tomorrow we got Babbia 122. Will be nice and spacious. We'll have tons of board space, so that'll be fun. But tonight we gotta be conservative because we got a tiny bit. But anyway, so now we're back here. We have y's, we have x's, we have our c. The last thing that we have to do is we have to get our answer in the form of y equals something. So now it's just algebra and moving stuff around at this point. So I'm going to take this -2, multiply it to the other side. This +2 I'm just going to change to a -4. And then this -2 goes away. Now, in order to get rid of the ln, I'm just going to raise both sides. I'm going to make each side the exponent of e. So I'm going to do e to that power is equal to e to that power. Because when I do e to the ln of something, it just equals that something. So now this left side is just going to be 6 minus 2y, and the right side is really weird, but I'm just going to rewrite it as is. It's e to the -4/3 of x plus 1 to the 3/2 plus c. Then subtract 6 over. So we have -6. That goes away. I divide by -2y, or by -2. And there's your answer. They might ask you to simplify something like the -6 divided by a -2 comes out to a 3, but if you leave this as your answer, that should be okay. They're not going to ask you to simplify an e to the exponent of something times something to an exponent. If you leave the answer like that, you should be good. You should get full credit for this question. I'm pretty sure that's exactly how I wrote it when I took it, and they gave me credit. Yeah. So does that make sense? Yes.
So when you're doing the separable thing, like this, like
Yeah.
a problem like this, you just want to solve for y?
Yeah.
That's literally it?
Yeah. And I just looked back at my test. I actually left it at this step, and they gave me full credit. Yeah, I didn't even simplify it out to the y equals, but it's a good practice to do y equals, because the whole point of the differential equation is we're looking for some function y that has a variable x. That when we plug in that function y into this equation, this becomes true. So we plug in y, we plug in the derivative of y, and we have some variable x. When we plug that in, it works. And as weird as it looks, when you plug this in for y, that equation's true. So that's why setting it in the form of y equals is what we typically do at the end of problems. But yeah, separable equations, that's what it's looking for. Again, just 3 basic steps. The tricky parts are in the algebra of getting it into the standard form. Then you might have some difficult integrals you have to take, but the actual differential equation steps aren't very involved for this one. It's more the other stuff. Does separable for first order make sense? I'm seeing head nods, so now we can go right into some exact equations. Now for the exact equations, I have a bunch of steps written out in my notes. I'm going to do all the steps, but I'm not going to write down each one, just because I'll email them out after so you can look at them in the notes. And I want to save a little bit of time. So I'll do all the steps, I'll say what they are, but I'm not actually going to write each one down. Okay, so we're going into some exact equations. So who knows what the standard form of an exact equation is? That's not good. Okay, so standard form. Does anybody remember anything about an exact equation? Okay, there's a dx term and a dy term. I heard an m and an n. We're right there. We got all the pieces. We just got to put them together to get a standard form. So we know we got an m and an n. I heard. We got a dx and we got a dy. Almost there. We just got to add some other stuff in. Just a couple extra characters, you know. So we add a plus sign right there. We added equals. We added 0, and we got a standard form. Look at that. We just pieced it right together. Just make it up on the test. You'll probably be right, you know. Somebody made it up at some point, so you just make it up on the test. And be like, no, I invented this during the test. We're good. But this is the way that they'll typically want to see it. They're not as imaginative. So we have m dx plus n dy equals 0. Now, what the hell is m and n? I know that's what you're asking. So I'm going to tell you. We have m is your partial f, partial x, and n is your partial f, partial y. Where f is some function that's in terms of x and y that it's going to give you, or that you're trying to find. You're trying to find what that f is, and it's telling you that if you take that answer, f, and you take the derivative with respect to x, you get that m. If you take that answer, you take the derivative with respect to y, you get that. So knowing those pieces of information, we can find out what that f is. And the way that we figure that out is we do the handy-dandy 8-step approach that I got written down in the notes. It's easier than AA. It's only 8 steps, not 12. So we're on the right track. Okay. So the first thing that you got to do is you have to check the equation to make sure that it actually is an exact equation. So I'm going to write down the example, and we'll go through each step one by one as we do it in the example. So I'm going to box that off. I'll start it right here. So the question that I had on my test was this. So we had a y squared plus 2xy plus 6x squared dx plus 2xy plus x squared minus 12y squared dy is equal to 0. And then it gives you some initial value that y at 1 is equal to 2. So they were nice to you. They put it in standard form for you. Because they gave you some function or some term times dx, another term times dy equals 0. So I know that right here is my m. I know that right here is my n. Now, so I said that the first thing that you have to do is check to make sure that it is actually an exact equation. And the way that you check that is you need to figure out what m sub y is, and if it's equal to n sub x, it is an exact equation. So we have to look at our m term, take the derivative with respect to x. So derivative of that with respect to x is 0. That is just going to be 2y. This is going to be 12x. Then we take the derivative of n with respect to x, and that's not right. It's just 2y. Right? I did that.
2y
plus 2x.
Yeah. 2y plus 2x. Okay, I just did that completely wrong. So we have derivative with respect to y. We have 2y plus 2x. That only has x's, so it's a constant. Derivative goes to 0. This is what our derivative of m with respect to y is. Now we take the derivative of n with respect to x and hope that it's equal to this. So derivative of the first term with respect to x is going to be 2y plus 2x plus 0. We know that our m sub y equals our n sub x. This is an exact equation. We can use this method. So the next step that we want to do after we prove that it's exact, we know that Gets a little check mark, so we're ready. The next thing that we want to do is, you can do this with either your m or your n. I like to do it with m because I just do it. I like to do it the same way every time, and I just like m better. So we have m, and we take the integral with respect to x. So we're looking at this term right here, and we're taking the integral with respect to x. The reason why we do that is because of this right here. That right there tells me that m is my answer, but I took the derivative with respect to x. So if I integrate with respect to x, I'll get back to my answer, which is that f. That's what I'm trying to find. So we integrate m, hopefully, and then we're going to get our answer. So I integrate this term with respect to x. So this first term, the y squared, becomes xy squared. My 2xy becomes x squared divided by 2, so it's just going to be plus x squared y plus x cubed over 3 times 6 is going to be 2x cubed. Now, just like any other time when you're taking your integral, you have to add a plus c. Now we have to account for some constant also. But since there's x's and y's in this, and we're only taking the integral with respect to x, there might be some term that's in our final answer that's like plus 3y squared. Where if we were to take the derivative, so we have a plus 3y squared up here. We take the derivative with respect to x, this thinks it's a constant, and it drops it out entirely. So there might be a term that only has y's, and we would never know. So instead of just adding a plus c, which is just plus a constant, we have to add plus g of y. Because there could be some entire function of y that gets dropped out. So this right here is our fxy. This is our answer that we're looking for. The only thing that we now have to find before we can be done with this problem is what is that g of y. The way that we find that is now using this other little helpful thing that we got written up here. That we know that our answer, or our n, is our answer with taking with the derivative with respect to y. So this is our answer. We're going to take the derivative with respect to y, and we're going to set it equal to n, and see if there's any term that fits in for that g of y. So we're taking the derivative of this with respect to y. So our f sub y is going to be equal to 2xy plus x squared. Derivative of that with respect to y is a constant, so it's 0. And then this is just going to be g prime of y. It's just the derivative with respect to y. Now the reason why we don't have to do a g sub y is because I know that this is only dependent upon y. So it's just g prime. It's just the regular derivative because it only has one variable in it. So if I did this correctly, this, my f sub y, should equal n. So I'm going to take this term, I'm going to set it equal to my n term. So we have 2xy plus x squared plus g prime of y is equal to 2xy plus x squared minus 12y squared. Now both sides have a 2xy, both sides have an x squared, but this side has a negative 12y squared, and this side has our g prime of y. Yeah.
Can you go back to the fy step?
Up here?
Yeah, where did you get that from again?
So this is my answer f, but I take the derivative with respect to y. So I take this, my answer right here that I found in blue, and I just take the derivative with respect to y. Because I know that n is my answer with the derivative with respect to y. So I take my answer, take the derivative, and that's that. And it should be equal to n. So that's what I just did right here. I set them equal. I see a 2xy on both sides. I see an x squared on both sides. Now all I'm left with is a g prime of y is equal to negative 12 y squared. So now I have a way to determine what my g of y is. The only thing left that I have to do is take the integral, because this is a derivative, so we're going to take the integral with respect to y. My left side is going to give me just g of y. My right side is going to give me negative 12 y cubed divided by 3, so it's going to be negative 12 over 3 is negative 4 y cubed. And when we got this point, I said the only thing that we need to do in order to be done with this question is find g of y. We found g of y. So all that we have to do, take our g of y, erase that, plug in negative 4 y cubed, and we're done with this problem. That is our answer.
What about the initial condition?
Oh yeah, that's a part 2 of this problem. What did it ask me to find? Oh, okay. So when we have this right here, if it didn't have this initial condition, we would be done. But since it has that initial condition, it's asking you to find what is this f of xy at that point. So at this point, 1 comma 2, what does f of xy equal? So all you have to do once you get to this step is plug in 1 for x, 2 for y, and you'll get some value right here. So my f of 1 comma 2 is just going to be equal to 1 times 2 squared, which is 4, plus 1 squared times 2, which is 2, plus 2 times 1 cubed, which is 2, and this is just minus 4y cubed, so this is going to be 2 cubed, which is 8, 4 times that is 32, so we're going to have minus 32. You add all this together, we have negative 32, negative 30, negative 28, negative 24, so this is all equal to negative 24, and then your answer with the initial condition plugged in would just be, we have x y squared plus x squared y plus 2x cubed minus 4y cubed is equal to negative 24. And that's your final answer with the initial condition plugged in. Yeah.
When you take the integral of g prime y, do you not add a plus c at the end of that?
So the plus c is basically what that is. So you do add the plus c. The reason why I didn't add in my notes is because it normally gets absorbed into that right side. Let me see if I even did it on the test, because that's how they're going to grade it. Yeah, so like the way that you would normally write this is, and I think the way that I did it should be fine, because this f of xy takes place of that plus c. But if you wanted to do it, you could just write equals c. So you have your function of your x's and y's equals your c. Because when you do, you would have the plus c added right there, and when you add it on down here, just move it over to the other side, and you don't have to put a negative because it's still a constant, whether it's on one side or the other. And then this c turns into that negative 24. But that's why I said it's kind of absorbed in that f of xy. So it couldn't hurt to put it. If you had this f of xy here, I don't think they'll take off points. But it couldn't hurt to have the plus c. Any questions on exact? Seeing no hands, we'll move on to some linear. do I dare ask? Does anybody know the form for a linear, the standard form for a linear equation?
Y prime plus
Okay, so we got a y prime plus
E of x y
p of x times y equals
y.
Q of x. Q of x.
Q equals another function.
I like to write it as f of x, q of x, just any function of x on that right side. So we got this one. So I don't even need to do linear because we know the standard form. That means we're good, right? Yeah.
I can't see that. There's a function of x times y.
So it is y prime plus p of x times y is equal to f of x. No problem. And now this could be written as y prime or dy dx. Either one, it's the same thing. So this is right here is our standard form. So if we want to try and use linear, we know we have to get it into that form in order to be able to use this approach. Now, for this one, it's nice and easy too because there's also a form of your answer. So you have your standard form, and then you have your answer. So anytime you're using linear, whether they tell you to use linear or you decide it for yourself, your answer is going to be y equals 1 over mu of x times the integral of mu of x times f of x dx. And that right there is your answer. And your f of x is just that term that they give you or that you move the equation to be on your right side of your standard form. The only other thing that we have to find is this mu of x. Now, who remembers how we get that mu of x? Integrating factor, I like it, I like it. So the formula for that mu of x is just e to the integral of p of x dx. So this is where that p of x comes into play, because that's how we find what our mu of x is. So if you can remember these three formulas for linear, that's all you have to do, because everything else is outlined for you. If you remember your standard form, you know what term defines your p of x, you know what term defines your f of x. Using p of x, you know this formula, you can find mu of x. Using mu, you plug it into your answer, just take the integral and you're done. So the steps are outlined for you in these three formulas. Again, doing those steps is where the hard part comes into play, being able to take the actual integrals, taking this e to the integral of something and knowing the tricks for your rules of e to some power, different things like that. But if you can know these will at least outline the steps for you, and then you can try to actually do those steps. So I have, again, all of these steps written out one by one. I'm not going to write them down now just to save time, but I'll email those out in the notes. And if you swiped in, you'll have your email, and I can send it to you after. So the problem that I had on my test was dy dx is equal to 2y over x plus x squared cosine of x. And it said that our initial condition y of pi is equal to 2 pi squared. So what's the first thing we have to do with that? Standard form. I like that. I heard other mumblings and I think we're along those same lines, but get it into standard form. Because before we can do any of this, we need it to look like that. So right now I have my y prime on my left side, which is good. But now I need to get it p of x times y also on my left side. So what term is that going to come from? where is that p of x times y? The 2y over x is disguised, but that is my p of x over y. So I want that on the left side. I'm going to subtract that over. So we're going to have dy dx minus, now the way that I'm going to write this is just to make my next steps easier. I'm going to rewrite this as 2 over x times y. So that way I know this term right here is minus 2 over x. That is my p of x, because it's something in terms of x times y. And then on the right side, I'm left with my x squared cosine of x. So now I look at my standard form. I'm in standard form. That's good. The only thing that I need to find before I can just start plugging stuff into my answer equation is I need to find what that mu is. So I'm going to come over here, and we're going to find what mu is equal to. I know mu is e to the integral of p of x. So we have e to the integral of negative 2 over x dx. So this integral right here, negative 2 over x, we have negative 2 times the integral of 1 over x dx. Just like we did in the first problem, the integral of 1 over something is just ln of that something. So we have negative 2 ln of x. It's technically the absolute value of x. So that is what our integral comes out to. But then that is in the exponent. So we have e to the negative 2 ln of x. Now, I can't do anything with that right now, because if I had e to the ln of something, then I know the answer would just be that something. But I have e to the negative 2 ln of something. So I can't just do that simple trick yet. But I know my log rules, and I know if I have a constant times the log of something, I can just take that constant and move it into the exponent of whatever in those parentheses. For this type of question, log rules are important, because I can't guarantee it, but I'm going to say 75% of the time when you have a linear problem, probably more like 90% of the time, when you have a linear problem, you're going to get an ln up here. So that way when you do e to the ln, it'll cancel out and you're left with just a polynomial as this term. So knowing log rules, knowing exponent rules are very helpful for your linear problems and then your Bernoulli problems, because they're very similar. So this becomes e to the ln of x to the negative 2, which is just x to the negative 2. And that is our mu of x. So we have mu is equal to x to the negative 2. So now I can take that and I can plug it in to my answer. Now, I know they tell you multiply everything by the integrating factor, and then this simplifies out with that. I don't like all those steps. It's just confusing. You don't need to write them down. You don't need to know them. It's just things to confuse you. So now that we know mu, we know what our f of x is. Plug right into that formula right there. So I have y is equal to 1 over mu. So 1 over x to the negative 2 is just going to be x squared. That's coming out faint. So we have y is equal to x squared times the integral of mu of x, which is x to the negative 2, times f of x, x squared cosine of x dx. Now look how nicely that works out. X to the negative 2 and x squared divide out. all that I'm left with in here is the integral of cosine of x, which I know is integral of cosine of x is just going to be sine of x. Plus c. Can't forget the plus c. Now the reason why I put it in parentheses like that is because the x squared is being multiplied by this whole integral, and from the integral is where you get the plus c. So the x is being multiplied by that plus c. So the last thing that we have to do is plug in our initial condition. So we know that when x is equal to pi, y is equal to 2 pi squared. So we have 2 pi squared is equal to pi squared times sine of pi plus c. Anybody know what sine of pi is? Thank you. So we have 2 pi squared is equal to pi times c. Hopefully we can figure out that c is equal to 2. So our final answer, I'll write it right here, we have y is equal to x squared times the sine of x plus 2. And that's our final answer. Does linear make sense? Okay, because linear is extra important because it also becomes involved when you're solving Bernoulli. So whether they give you a linear problem or a Bernoulli problem, you're going to need to know these steps. Odds are that they're not going to give you both, just because they're not going to ask you to do the same thing twice when it's a long final, but know these steps because you're going to have to use them at least once. With that being said, if there's no questions on linear, we'll jump right to Bernoulli. You're making great time. Look at that.
I know why.
But don't worry.
I think we will say, I believe.
Yeah. Well, like, he doesn't do like a go to his office. I don't think so. He does that. To meet the people. I have 2 days on, I don't care about where. I go after we're getting a pizza party tomorrow.
Yeah, that is the same thing.
My second to last day. And I don't think my boss would know that if I didn't just tell him on Monday, my last day. Okay. So we're going to get into some Bernoulli equations right now. So, who knows what question I'm going to ask? What's the standard form? X squared, that's Cauchy-Euler we're going into. That's like second test type stuff.
Is it the same thing but fxy? Like
You're gonna have the y to the n.
There you go. So you were like you were missing one little thing, but like you were closer than anybody else. Okay, so standard form for Bernoulli. Standard form for Bernoulli. We have dy dx plus p of x times y. Looking familiar so far. Times f of x. The only thing that's different between your standard form for Bernoulli and your standard form for linear is you have a y to the n at the end next to your f of x. Only thing that's different. So this right here is our standard form. Now, the best approach, I don't remember how they teach it to you guys. I think some professors teach it this way, some professors teach it a different way. But the best way to solve this, in my opinion, is you convert it from Bernoulli to linear, then you solve it as a linear equation, and then you plug back in what you took out in order to make it linear. Because we've done linear enough that we know how to solve that, so we just change this to linear, solve linear, and then just like count for it at the end.
Do you think it's like safe to say that since they wouldn't give us both, they'd probably just give us Bernoulli because it's harder?
That's safe to say, because you're going to have to do the linear steps in the Bernoulli.
Okay.
And I think that's what they did, like when I took the test, we only had a Bernoulli, we didn't have a linear. I don't know if that was the same for y'all. Yes, no? Okay. I didn't expect you to, I was just told. Okay, so, similar to how I did all the other ones, I'm going to jump right into the problem, and I'm just going to explain the steps as I'm doing each one. So, the problem that it gave us, oh wow, it's really nice. It gave us dy dx plus 1 over x times y is equal to y squared. And then we have the initial condition, y of 1 is equal to 1/3. This is the example. This is what they gave us. This is the one that I had on my test when I took it spring 2016, question 3. So, just looking at this, is it in standard form? Yes. So, we know that it's in standard form because we have dy, we have some function of x, times y, times another function of x, which is just 1 in this case, so they make it a little easy on us, and then we have y squared. So the first thing that you want to do is, it's helpful to like explicitly identify what your p of x is, what your f of x is, what your n is. So we're just going to write that down here to save us some time later. So we know that our p of x is just equal to 1 over x. We know that our f of x is just equal to 1. And we know that our n is equal to 2. Because our formula says we have y to the n. Over here we have a y squared. So we know that n is equal to 2. So what we're going to do with that, what we want to do is you want to set, so we're going to be introducing a new variable here. I like to use v. And v is what we're going to use to change this into a linear. And then at the end, we're just going to plug back in for v, so that way we can solve our answer in terms of y. Okay? So what I'm going to say that v is equal to y to the 1 minus n. Okay? Now this is just something that you're introducing. You could use w for this, you could use u, whatever you want, but v is equal to y to the 1 minus n. So in this problem, since n is 2, I know v is going to be equal to y to the negative 1. So the whole idea is I want to be able to plug in my variable v for everywhere that I see a y and a dy in my equation that I started with. So right now I have v is equal to y to the negative 1. I want to solve for it in terms of y, so I can plug back in up here. So all I'm going to do, this is really v is equal to 1 over y, so I'm just going to flip both sides, and I have 1 over v is equal to y. And then I also have a dy dx that I want to be able to substitute in. So what I'm going to do is I'm going to take the derivative of both sides with respect to x. Yeah. No, I'm going to take the derivative of y with respect to v. So, right now I'm just going to bring it over here. We have 1 over v is equal to y. I take the derivative with respect to v. This side just becomes negative 1 over v squared. This side just becomes dy dv. Right? You're just taking the derivative with respect to v. This step, it's a little confusing, but it makes sense. Because we know that if I multiply by the same thing on both sides, it doesn't change the value, right? Is that a question?
Yeah, what's the purpose of using v? Like, what do we want to do?
So, by putting v into this equation and setting that situation, if you do everything else correctly, we're going to turn this into a linear problem. Where instead of having y, we have v. And then we can solve it in terms of v, and then plug back in this case. Everywhere we have a v in our final answer, we plug in a y to the negative 1, we just flip it and we have our final answer. Yes?
So for every Bernoulli equation, you have you substitute the v equals y 1 minus n into it?
Yep. Anytime you see a Bernoulli, this is how you're going to turn it into a linear. You say v is equal to 1, or y to the 1 minus n, and then you carry out these steps that we're doing, and if you do it correctly, it'll turn into a linear. So the first step, we plug in our n, then we find y equals something in terms of v. We take the derivative with respect to v, and then the next thing that we do, because the reason why we're taking the derivative is we want to be able to plug in for this dy dx. So like I was saying, if you multiply by the same thing on both sides, it doesn't change the value. So we're used to multiplying fractions on both sides to cancel things out, make it look different. So if I multiply by 2/3 and 2/3, I'm not changing the value. So what I'm going to do is I'm going to multiply both sides by dv dx. Now, it's a little bit more confusing than multiplying both sides by 2, but I'm still multiplying both sides by the same thing, so I'm not changing the value. But what that allows me to do is on this right side, I now have a dv on top and a dv on bottom. Those will divide out, and this right side I'm left with dy dx. So I'm just going to rearrange it. I have dy dx is equal to negative 1 over v squared dv dx. And what that now allows me to do is where I have a dy dx, I can plug in this stuff on the right side. Where I have a y, I can plug in that, and my y, I can plug in that again. Which means I can now eliminate y from this problem, and then turn it into something where I only have v's and x's. So, I'm going to plug in that stuff. So, for dy dx, I'm plugging in this. So dy dx turns into negative 1 over v squared dv dx plus 1 over x times y, where y is 1 over v, is equal to y squared, or 1 over v squared. So now you're looking at that and you're like, that's not really simpler, right? Because it looks weird. But I'm telling you that if you do all these steps correctly, this is the form of a linear. The one thing that you have to do in order to turn into the form of a linear is I can't have anything out in front of this dv dx. So I'm going to multiply by negative v squared. So that way this first term will have this negative 1 over v squared go away. So I'm going to multiply every term by negative v squared. Those cancel out. I'm going to multiply by negative v squared. And I'm going to multiply by negative v squared. And what that does, right here, I'm left with a dv dx. Here, I'm left with, I still have that 1 over x. Bring the negative, oh no, the negative's going to, I bring that negative out in front, and I have a v squared over v. So that just becomes v. And on this right side, I have a 1 over v squared. I have a v squared. That becomes 1, and I just have that negative left. Now, does that look familiar? I have dv dx minus 1 over x times v is equal to negative 1. That is in the standard form for a linear equation. And if you do these steps, this is the key step. If you set v equal to y to the 1 minus n, you substitute all of your v's in for your y's, that is what you'll be left with. You'll be left with a linear problem in terms of v instead of y. Now, we're going to solve this as a normal linear problem, just like we did the last one. We're going to get something v equals an answer. And then when we get to that step, we're just going to plug in, wherever we see a v, we'll plug in y to the negative 1, and then solve for y equals, and we're done. So, I know that the first thing that I have to do, or first thing that I'm going to do, is identify, I know my p of x is equal to negative 1 over x, which is that term right there. And I know my f of x is equal to negative 1. So with that, I'm going to first find what my mu of x is, so that I can plug it into that answer formula that we wrote down in the last problem. So I know that mu of x is equal to e to the integral of p of x dx. So my integral of negative 1 over x dx is just going to be negative ln of x. And notice how, again, we're left with that ln of x. I take this negative, I move it into the exponent of the x. So my mu turns into e to the ln of x to the negative 1. Which means my mu is just equal to x to the negative 1. So now that I have that, I'm going to use just this left half of this board right here. Now that I have my mu of x, I have my f of x, I can plug into my answer formula. And my answer formula said that last time we used y, but now our variable is v. So we have v is equal to 1 over mu times the integral of mu times f dx. So v is going to be equal to 1 over x to the negative first is just x, times the integral of x to the negative 1 times f of x, which is just negative 1, dx. Now that negative 1 I can just bring right out in front. And all I have in here is just the integral of 1 over x, x to the negative 1, 1 over x. So I'm going to have v is equal to negative x times the integral of 1 over x is just ln of x. Right. Don't forget the plus c. So now we have our answer in terms of v, right? So if this was a y, the only thing we would do is plug in our initial condition and we'd be done. So we have our answer in terms of v. The only thing that we have to do in order to get it in terms of y is plug this in right here, because I know that v is equal to y to the negative 1. So I just substitute that in. I have y to the negative 1 is equal to negative x ln of x plus c. Now, since we don't want the answer in terms of y to the negative 1, this is really 1 over y, so I can just flip this and flip the other side, because this is really 1 over y is equal to this. So I can just take the reciprocal, y is equal to 1 over negative x times the ln of x plus c. Does that make sense? So this whole problem, the only thing we did was solve a linear. We just substituted in a different variable to make it a linear. We solved the linear, and then we substituted our y back in. Now the last step that we have to do is account for this initial condition that they give us of when x is equal to 1, y is equal to 1/3. So I'm going to bring it right over here just for the sake of space. So right now I have y is equal to 1 over negative x times the ln of x plus c. When I plug in 1 for x, I know that my y is equal to 1/3. So I have negative 1 times the ln of 1 plus c. ln of 1, 0. So I have this ln of 1 goes away. I'm left with negative 1/3 is equal to 1 over negative c. Anybody, what's c?
I mean positive 3.
Yeah, I got confused by that too. So c is equal to 3. We can plug that c equal to 3 in right over here. And we have y is equal to 1 over negative x times the ln of x plus 3.
Okay.
And we solve the Bernoulli.
It's negative 3.
Isn't it positive 1/3 on that side?
It
So
is
it'd be
positive
negative 3.
1/3. So it is negative 3. No. Yeah, that should be positive. So then that is negative. And this is a minus. Yeah, that's what I had in my notes. Does that make sense? So what I did right there was I'd accidentally made that negative. So I know that this c has to be a negative 3. So this is y equals 1 over negative x times ln of x minus 3. Are there any questions on Bernoulli? Yes. There might be another way that some of the professors taught it. So I remember learning it a different way from Miller, but I never used that because once I learned this way, this was much, much easier. So I don't even know the other way that it's taught because I've only ever done it this way. So if you want my help, do it this way. But does this make sense? Does these steps make sense? Because if you can understand the substituting in for v for y, then it's just a linear. And we can just use those 3 equations that we had for linear. Okay, I'm going to go into some homogeneous now, if we're all good with that.
Jay, are you undetermined coefficients? So wasn't that test two?
I said, if we have time, it's like, I went through all that stuff relatively quickly, so like we can do that stuff if people want to. Or you don't have to. If you don't want to, you can do it tomorrow. You can do whatever. Okay. So now getting into some homogeneous equations. The whole idea with homogeneous equations is there's three different possible forms of answers you can get. Now you should be very familiar with those three different possible forms because all of eigenvalues, having to test case 1, case 2, case 3, is because of there's three possible forms of answers that you can get when you're dealing with homogeneous. Yeah, I know, nobody likes eigenvalues, but we all gotta do them, you know? Just wait till you get to multi, when you have to do multivariable eigenvalues, that's when it gets tough. But that's next semester, don't worry. Unless you're an EE, then you don't have to. Anyway, so one case we could have is we solve our auxiliary equation. And then from that auxiliary equation, we get some M1 and M2. And both your M1 and M2 are real. They're real and unequal. So you get M1 equals 3, M2 equals -2. They're both real numbers, they're not the same. The answer that your form would have, this is the most common, that you use the most often. Your answer is in the form of y is equal to c1 e to the m1 times x plus c2 e to the m2 times x. That should hopefully look familiar. Another case that you can have M1 is equal to M2, and they're both real. Now, if this is the case, your answer is going to be in the form of y is equal to c1 e to the m x. I'm only writing m because you only end up having one. Plus c2x e to the mx. Because we can't have two terms that are the same exact thing, so the way that we account for that is we multiply this second one by x. Now the third case that we can have, which is where all the fun comes in when we're dealing with our eigenvalues, is if m1 and m2 are imaginary. Because if they're imaginary, we get some weird stuff going on. So assuming that they're in the form of m is equal to alpha plus or minus beta I, the way that your answers would look would be y is equal to e to the alpha x times C1 cosine of beta x plus C2 sine of beta x. Now, a lot of times in your eigenvalue problems, this alpha is just 0, so you don't have this first term. You just start off with your C1 cosine of beta x plus C2 sine of beta x. But if you do have something, some constant that's out in front of this plus or minus, then you'll have your e to the alpha x out in front, then times everything else. So these are the three possible forms that your answer can take. And again, this is where your three eigenvalue situations come from. Now, this is all based on what M1 and M2 are. The way that we find what M1 and M2 are come from our homogeneous equation. So I don't have a specific homogeneous equation written in here because it's like in other problems, but I can make one up easily. It might not turn out well, but say we have a y double prime plus 2y plus 4 is equal to 2x cubed. If it's asking me to find the homogeneous solution to this, I can ignore this right side because homogeneous means that it's equal to 0. So I take this, what I have on the left side, and I set up my auxiliary equation. And the way that I do that is, some people use m's, some people use r's. I like to use m's. So since I have a y to the second power, I do m squared plus, I carry down that coefficient of 2 times, since I have y to the first derivative, it's just m, plus 4. And then I set that equal to 0.
Is the y the first derivative the second term, or is that
Oh,
just
yeah,
second
yeah,
derivative?
that should be. And then
Y.
it should be
Then that's what
that. Yeah. That's what it looks like. So this is your auxiliary equation from this left side. Again, that right side, the 2x cubed, doesn't matter because in homogeneous we're assuming that it's equal to 0. So you set up this auxiliary equation. This is not going to work out nicely, but we now need to solve for what M1 and M2 are. So I look at this, I can't factor that, so I have to go into some quadratic. So I'm going to say that M is equal to -2 plus or minus the square root of 2 squared minus 4 times A times C all over 2A, which is 2. And that's just right there, the quadratic formula. X equals negative B plus minus square root B squared minus 4AC all over 2A. You never learned that song for the quadratic formula?
I'm so glad I got that on film.
So that's the quadratic formula if you ever get something weird that you can't factor, which might happen. And what we're going to do with that, we know that 2 squared is 4, minus 16 is just going to be -12. This is really bad. So we have m is equal to -2 plus or minus the square root of -12 over 2. So I know the square root of -12, I can factor that into a radical 4 and a radical 3. So it's just going to be 2 rad 3. So I have m is equal to -2 plus or minus 2 rad 3 I over 2. So I'm just going to divide the 2 out here, make this a 1. And I'm going to divide that 2 out there, make it a 1. So now my m's are equal to -1 plus or minus radical 3i. So since that is what I got for my two m's, -1 plus rad 3i, -1 minus rad 3i, I know that those are imaginary, so I can write my answer in this form. So I'm going to write it right over here just because I don't feel like bending down again. So we're going to have y is equal to e to the alpha x, where my alpha is that -1 out in front. So I have e to the -x times c1 cosine of beta x, where beta is my radical 3, plus C2 sine of beta x, and that is the form that your answer takes. Now, if they gave you some initial conditions, you can plug in for your C1 and your C2. In this one, I don't give you initial conditions because I just made it up. So that would be your general or your homogeneous solution to this problem. Now, if it asks for general solution, you can get into some variation of parameters, undetermined coefficients, but we haven't done that yet.
Do you expect them to give us a problem that's just homogeneous, or is it just
No.
gonna be part of everything else?
No, they're homogeneous is going to be part of everything else. Like there might be an undetermined or a variation of parameters that the first step it says solve the homogeneous equation. But they're not going to give you just a homogeneous by itself. Does that make sense? Question.
For the original question, when it's set equal to like an f of that, like an x squared, yeah, that. Do we ever have to do anything with that? Like, that just kind of goes away.
So if it asks for a particular solution, that's when the right side comes into play.
Particular solution.
Yeah. So you find the particular solution using your variation of parameters or undetermined coefficients.
Oh, right, yeah.
But if it's just asking for the homogeneous solution, which is what I was asking for, the right side doesn't matter. Now, I can explain it to you what's physically happening in terms of circuits, but that'll probably just confuse you more and give you traumatic memories from this morning, so I'm not going to. See? But this is your driving force behind your current or whatever's going on. But in your homogeneous, you don't care about your driving force, you care about what's going on this left side. So you ignore the right side. The particular solution is where that right side comes into play. Does homogeneous make sense? And it'll make more sense when you're doing other problems where it's the first step of variation of a undetermined coefficients of, I guess, Cauchy-Euler. There's a different type of homogeneous. But does this all make sense? Question.
Can you put a little if you ask if it's a substitute so you can set that equal to your right side? And then
It depends. Depending on what that side, that right side is. So like this right side, I would definitely use undetermined coefficients. But if it's something different, you would use variation of parameters. And from everyone, or some people packing up, it sounds like people are done for tonight. Or do you want me to go into, I can do variation of parameters, or undetermined coefficients, or both, or neither? We have a both? We want to do that tomorrow? So, we have a vote for one today, one tomorrow? Just tomorrow? If you want to stay, I'll go over it. If you want to leave, feel free to leave, go to midnight breakfast, enjoy some food. If you didn't swipe in on your way in, please swipe in. If you don't have your swipe, type in your ID number and hit enter. Midnight breakfast, yeah, you need your swipe. But it's free. Yeah, you just need the card. It's free. Question.
With the email that you're sending us, is there going to be a review for a video for review 2 and 2?
I think I have a video from review 3, either me doing it in the past semester or Pat DiPaolo doing it from the past year. Test 3 I know I have a video of, and then I'll resend out the PE 4-year series that Pat did. Like,
Shoot me a text with whatever videos you need. I'll send them to you.
what was that?
Whatever video that you send me a text. Because I have
Well, no, like, I'm pretty sure we have them all. I just have to look through my folder, and because I have all the links saved as like Word documents. But if I need anything, I'll let you know. Thank you very much.
don't want you to see it, Kevin. I don't want you I'm just saying. It's like you're going down. Oh, yes. Go. Do something. Just left. Maybe just read the whole sheet. This is like
Okay, so now that we've lost all the dead weight, no, I'm just kidding. Just kidding. I said just kidding quickly enough that I cannot be held liable. But anyway, so we're gonna go over. Do we want to do? I'll do variation parameters and undetermined coefficients. I might as well. I'll do them more quickly than I did in the test 2 review, just because it's reviewing again this time. But is there one that people struggle with more over the other, undetermined or variation? We're bad at undetermined? Okay. So I'll do that one first. So the whole idea of variation of parameters and undetermined coefficients is accounting for that right side of the equation. So when I had that equation written up, that 2x cubed, you're welcome. Good luck on everything you do. In order to figure out what the effect that that right side of the equation has on the problem, you have to use one of these two methods. So we're going to start with undetermined coefficients. Now, undetermined coefficients is, I'm going to say, the less powerful of the two, just because it can only be used in certain situations. The right side needs to take a certain form in order for you to be able to use this. But if it is in one of those forms, it's much easier to use this than variation, because it's going to be simpler, it'll be less steps, and it doesn't involve integrals, which is therefore simple. So the 3 forms that your right side of the equation can take for you to be allowed to use this are, anybody know them? What's the first one? Or any one of them? Nothing. Nothing for undetermined? Okay, so the first one, it can be a polynomial. Now, a polynomial is just x squared plus 2x plus 3, or x cubed plus 3x plus 1. Yeah.
Are we doing undetermined coefficients now? Or?
Yeah. I wrote variation of parameters before we decided.
Wait, which one has more power again?
Variation of parameters you can use in any situation, but it might be more difficult to use it. So if you can use undetermined coefficients, we want to do that. Sorry for people writing in pen that had already written that down. Sorry. But anyway, the first type of form that right side can take is a polynomial. And like I said, that just means there's no fancy things in there. It's just x to the power of something and constants in there. So if that is what we have, then our answer is going to be in this form. Can we see the orange? So our answer, our y particular, is ax squared plus bx plus c. Now, the way that you determine, it's not always going to be ax squared that's the first term. Whatever the highest power of that right side is, that's what you start with. So if on your right side of the equation you have a 2x cubed, this would be ax cubed plus bx squared plus cx plus d. Whatever the highest term is, you start with that one, and then you work down by 1 each time. Even if the equation only has an x cubed, you still have to include in your particular everything from that down. Now, you didn't know it before, but maybe your memory was jogged. What's another type of form that that right side of the equation can take?
Exponential.
Exponential, yes. So we can have an exponential. Specifically, it needs to be in the form of e to some power. It needs to be e to the x. It can't just be anything to the x. So if we have that right side of the equation being our exponential, then our answer is y particular is equal to a e to the, so I'm going to say if we have e to the alpha x right there, we have e to the alpha x right there. The purpose of me throwing in that alpha is if you have e to the 3x, then this has to be a e to the 3x. This one's the simplest form because it's always going to be just that one term of whatever your e is, just throw an a out in front. Anybody want to guess what the last one is?
Trig.
Trig, so sinusoids. Let's go. We're getting good at this. It's as if we're learning. So we have our sinusoids. So sinusoids meaning our sine or cosine. And this is going to be in the form of cosine, I'll say beta x. Now if the right side of our equation has that, then our answer takes the form of y particular is equal to a cosine of beta x plus b sine of beta x. Now whether you have just sine, just cosine, or both on that right side, you have to include both cosine and sine in your answer. And again, if you have cosine of 2x, you have a cosine of 2x plus b sine of 2x. So these are the three possible forms that that right side can take, and these would be your three answers for y particular. Yes.
What if you had something like x squared plus e to the alpha x? Could you just add them together?
So if we had x squared plus e to the, we'll say, 4x, find an answer for this, find an answer to this. Since they're added together, we add them together. If we had x squared times e to the 4x, if it was something like this, we couldn't do because that doesn't follow these guidelines. This you would have to use variation of parameters. But since it's separated into terms here, where one term is good, the other term is good, we can find the answer for this, and then just add them together.
I thought you could do products of any of those three.
See, that's what I was thinking. I think you can.
Would you just multiply it by e to the 4x?
That's what I'm thinking. This one in particular would just be annoying because you get a lot of terms. But yeah, this one would be easier to do variation of parameters, but you probably could find the answer of one, find the answer of the other, and multiply them together. It would be annoying, so I don't suggest doing it, because it'd probably be easier to do variation with that, or with something more complicated like that. But you can use undetermined coefficients for this. Find an answer for this, find an answer for that, and just multiply them together. Make sense? So now, and then the one other thing to keep in mind is, say in my homogeneous solution, I get something that has an e to the 3x in it, and my particular tells me to have a e to the 3x. I can't have a term in my particular match something in my homogeneous. So the way that I account for that is I'm just going to take whatever term is, I'm going to multiply the entire answer by x. Because that's going to make this a different term from what it is in my homogeneous. So that way I'm not going to have any overlap. And I don't like overlap because then it messes with the problem. Yeah.
You multiply the particular that you found by x, so like the one that you make up, the AE to whatever you multiply
Yes.
that by.
You multiply that by x, and that'll account for that term already being in your homogeneous. Okay, so with that, I'm going to jump into a problem. And this one's, it doesn't involve that last question that you asked, but it involves the idea that there's polynomials and exponentials in this. So, this is from my test, spring 2016, question 1. It says, find the general solution of this. Y double prime plus 9y is equal to 81x squared minus 18x plus 26e to the negative 2x. Okay, so what's the first thing that we have to do when solving this problem?
Solve the general.
We're looking for the general.
I mean, do the left side of homogeneous.
Yeah, solve the homogeneous first. Before you use variation or undetermined coefficients, we have to solve for the homogeneous first, because your answers for the second parts, for the particulars, are going to be based off what you get for your homogeneous. So, I ignore everything on the right side. I'm going to make my auxiliary equation, which is going to be m squared plus 9 is equal to 0. This one, subtract 9 over, I'm going to have m is equal to plus or minus 3i. With that, I plug it into my form of the answer for an imaginary. So I have y homogeneous is equal to, I don't have an alpha in front of the plus or minus, so I don't have to do e to the alpha x. I just start with c1 cosine of 3x plus c2 sine of 3x. And that's your homogeneous solution. Now we can go into our particular. So now we account for this right side of the equation. What form does that fit? Which of the three over there does that fit? So we have a polynomial because we have an x, we have a coefficient x squared minus 18x.
Also have an exponential.
We also have an exponential.
So you add them, right?
Yep. So we're going to find the answer for one, we're going to find the answer for the other, just add them together, because it works like that. It's nice. So my y particular, I see I have an x squared, that's my highest power of x, so I have to start at a, x squared, and work my way down, plus bx, plus c. And then I have an exponential, so I'm going to do plus d e to the negative 2x. That works? Now, if this term right here was plus 26, let me do it a different color. If this said plus 26 sine of 3x, then my particular solution would have to have, instead of this d, it would be plus d sine of 3x plus e cosine of 3x. And if that were the case, I would have a problem. Because now my homogeneous has a cosine of 3x and a sine of 3x. And I have both of those same terms in my particular. So this would be a case where you have to multiply by x. So since these are the offending terms, it's only from my sinusoid terms, I only multiply these by x. So I would throw an x in here and throw an x in here. And then I would continue on the problem from there. Does that make sense? That's how I would account for the fact that I have my sine of 3x and my sine of 3x already in there. But we don't have that, so we're erasing that. And we're continuing back in orange with the problem. So now the whole point of doing undetermined coefficients is, right now, this is the answer to the problem that I want. So like, it's asking for a y that we can plug in here. That's my y. That's my answer. The only thing is, I don't know the coefficients for each of these terms. One might say they're undetermined. See what I did there? But I'm saying that that's my answer. So if I have my answer and I plug it in up here, it should work, right? So let's do that. So I'm going to plug in this y up here. The only thing is, I need to take the second derivative of it before I can plug it into that original equation. So I take the second derivative, or first I have to take the first derivative. This is just going to be 2ax plus b. The derivative of a constant is a constant. This is going to be minus 2d e to the negative 2x. Now I take my second derivative. It's going to be yp double prime is going to be 2a plus 4d e to the negative 2x. Now using that and that, I can plug it into this left side, set it equal to the right side, and I'll be able to find out what those coefficients are. So I'm going to erase this. So plugging in my y double prime, I have 2a plus 4d e to the negative 2x plus 9 times my y, which is ax squared plus bx plus c plus d e to the negative 2x is equal to my right side, which is 81x squared minus 18x plus 26 e to the negative 2x. So now, what is this similar to what we just did? Similar to partial fractions, I now have an equation with some a's, b's, c's, and d's on one side, and some matching terms with actual coefficients on the right side. So what I'm going to do is I'm going to look at all the terms that have an x squared. Every term with an x squared on the left side, I'm going to set that equal to every term with an x squared on the right side. So on the left side, I'm going to go through and I'm going to look at my x squareds. That doesn't. Oh, here I have a 9ax squared. So then I'm going to cross that out. And that's all my x squareds on the left. On my right, I have 81 x squared. And I'm not putting the x squareds in here because I just care about the coefficients. Because the coefficients for all my x squareds on the left should equal the coefficients for all my x squareds on the right. So that's what I'm left with. Now I'm going to look at the coefficients for all my x's. So on the left side, I have, or 9b, and that's all I have. So that's going to be equal to negative 18. Then I'm looking at the coefficients of all my constants. So constant, I have 2a, plus 9c, and then on my right side, I have no constants, so it's just going to be equal to 0. And then I'm going to look at everything that has an e to the negative 2x. The left side, I have 4d plus 9d, 9d, not the number 90. And the right side is 26. So a, nice and simple, we just divide by 9. We have a is equal to 9. This one, we just divide by 9 again. We get b is equal to negative 2. Here we add these two terms. We have 13d equals 26. So we get d is equal to 2. And here when we plug in, because we want to find c, we're going to have 18 plus 9c is equal to 0. So we get that c is equal to negative 2. Make sure it's all the same numbers. We got 2, we got 9, we got negative 2, we got negative 2. Beautiful. So, when we found this, I said this was our answer. The only thing that we still had to find was our coefficients. I just found my coefficients. So I'm just going to take these, plug them in right here. My a is 9. My b is negative 2. My c is negative 2. And my d is positive 2. And that right there is my answer. For my particular solution, the question asked for the general solution, so how do I find the general solution? Add them together. Add your homogeneous, add your particular. You don't have to write it all out most of the time. If you have time, you can. Like these are relatively short terms, so you can just write like yg equals c1 cosine 3x plus c2 sine 3x plus 9x squared, all that. But something that I know that they also accept most of the time is you just write yg is equal to yp plus yh. Box that, and as long as you have this labeled as yh and that labeled as yp, they'll accept this. Now, that's a little risky to do because in some situations, you'll have a term from here that is a like term to a term from here, and they'll combine, and then you have to simplify. But most of the time, that won't happen, so this will be good to go. So if you're short on time, pressed on time, and there's like 8 terms in this with like fractions and crap that you don't want to have to write again, if you write yg is equal to yp plus yh, you have each one labeled as yh and yp, you should be good.
Can't you not have like terms, because if you have like terms, you multiply it by an x?
I think it happens more in variation of parameters, but it does happen rarely. I know there's a problem. It might be the one that we have for variation of parameters. No, I know there's a problem that I've done in one of my reviews that has that situation where you end up having like terms. Is that another question? No? Okay. Does undetermined coefficients make a little bit more sense? Do you understand the situations when you're allowed to use it? It has to be one of the 3, polynomial, exponential, or sinusoid. And if it is one of those 3, you could use undetermined, you could use variation of parameters. If I wanted to, I could have done variation of parameters for this. But it would have been very difficult. It would have been annoying integrals, possibly integrals that you can't take by hand. It would have taken a lot longer, and your life would be even more hell than it currently is. So, if you can do undetermined coefficients, it's best to do undetermined coefficients. But you might ask, what happens if we can't do undetermined coefficients? That's what variation of parameters is here for. And we'll do variation of parameters, and then we'll call it a night.
I should get that like so use it so much. That's the sound you I use it so much. You like an easy mode.
Yeah, they give us one, and we have to pick which one to use, or they give us one of each.
I don't think they're going to give you one of each. I know on the tests, like during the year, I think they normally give you one of each.
They did.
I feel like on the final they're not going to. That's just a hunch. Completely making it up. I could be completely wrong.
Okay, but we will have to like know that.
Yeah, you'll have to know. You'll definitely need. If they're really nice, they'll say solve using undetermined coefficients, solve using variation of parameters. But I don't expect them to be nice because on the final it should be, you know how to do everything. Now the difficult part is figuring out how to solve each problem, like what method to do for each problem, which can be difficult at times. Because you have to see the form of the problem and what it fits. Yeah. Yeah. And then my recommendation for that would be look for your polynomials, look for your sinusoids, look for e to the something. A lot of times when it's going to be a variation of parameters problem, you'll see like a 1 over x squared. Because if you have any variable in the denominator or fraction, that you cannot do undetermined coefficients. Because when you would take like the first derivative, second derivative, it gets very different form. The reason why the three forms of polynomial, sinusoid, and exponential work is because when you take successive derivatives, it's very predictable what form it will be. So I know when I have an x squared, it's going to go to a 2x, and it's going to go to an x, and then it'll go away, or it'll go to a 2x, then a constant, and then it'll go away. If I have a sinusoid, it's always going to rotate between sines and cosines. If I have an e to the x, it's always going to be e to the x. If I have a 1 over x squared, when I take the derivative, it's going to be negative, and then I'm going to have higher numbers on bottom, and then it's going to get even more on. It's very hectic.
Okay, so if it's a fraction.
So if it's a
denominator, it's always variation.
even if it's 1 over x. If you have a variable in the denominator, that's a very common thing that they do, that you'll have to do undetermined coefficients. Also, if you have like an ln of x, that's something that you can't use undetermined coefficients for. So any of those weird things that they can throw in there should be a hint, bells and whistles should go off to use variation as opposed to the undetermined coefficients. So now, going to variation of parameters, and then we'll be done after a nice long night of some differential equations.
I died. That was the morning round. Yeah, I didn't even open it to look at it, I just do it. You know, I was like, I'm gonna start crying back. Come to daddy. I immediately got it.
All hell pays God.
I'm gonna go back and watch the video now. Yes, yeah. I saw it at 6 in the morning, I'll be like, I didn't open it either. I was samurai. I opened this other time. This saw like the screen of it.
Okay. Last topic of the night, and we can go to sleep. Or get some food, then go to sleep. So these are really the 4 important things to remember for variation of parameters. So the first thing, you got your answer. Your answer is going to be in the form of u1 times y1 plus u2 times y2. That seems relatively simple. Unfortunately, it's not. Because there's no formula that tells you what u1 is. There's something that tells us what u1 prime is. So we know that u1 prime is negative y2 times f of x over a times the Wronskian of y1 and y2. And u2 is very similar to, or u2 prime is very similar to that. The only difference is you have y1 here and it's not negative. I'll explain. Question?
Yeah, don't we integrate this or not?
Yeah, because in order to get from our u1 prime to our u1, that's where the integration comes in. And this a value is when you're given your equation, if you have some term in front of your y double prime, then that's what that a is. Whatever the coefficient of your first term is, you put that a right there. Okay? So I'm going to jump into a problem. We're going to do it. We're going to be happy. I'm going to leave. So we have y double prime minus 2y prime plus y is equal to 1 over t e to the t. And it just says t is greater than 0 because time can't be negative. So, and it just says find the general solution. It doesn't specify what one to use or the other. So first question, how do I know that this is going to be a variation of parameters problem?
Multiplying.
Because I have a 1 over t. Because this does not fit the form of one of my polynomials. Because that's t to the negative 1. I can only have a t to a positive power for a polynomial. So, second question. What do I do first? Find the homogeneous. Thank you. So my homogeneous is going to be m squared minus 2m plus 1 is equal to 0. This simplifies into m minus 1 squared is equal to 0. So m is equal to 1. So since my m1 and my m2 are equal, I know that I'm going to be in the form of y homogeneous is equal to c1 e to the m, which is just 1x, plus c2 x e to the x. That's my homogeneous. Now, for variation of parameters, doing your homogeneous first is even more important because in order to do any of this stuff, you need things from your homogeneous. Because I explained where you get your u's from, where you get the w's from, where you get the a's from. But this y1 and y2 that are both in this formula and in your final answer come from your homogeneous. Because the form of this homogeneous is yh is equal to c1 y1 plus c2 y2. So anything after your coefficient, your constant, is your y1, is your y2. So I know my y1 is e to the x, my y2 is x e to the x. And those are going to be important for all this stuff. So, first thing, we want this as our answer. So we need to figure, we have our y1, we have our y2, we need to figure out what our u's are. So I'm going to start at u1. So I know that u1 prime is equal to negative y2 times f of x over a times the Wronskian of x. Now I'm going to plug in what I had for that. So my negative y2 is just going to be negative x e to the x times f of, I should be using t. Yeah, I'm just going to change these to t's. You know what, I'll just change these to x's, that'll be easier. Okay, so this will just be negative x e to the x. All I did was just change those to x's because I wrote x's instead of t's.
Would the t is greater than 0 be x is greater than 0?
Yeah, like this, yeah, this doesn't really matter, but whether it's an x or a t, it's the same answer, it's just a notation of things. So I have negative x e to the x is my negative y2 times f of x is going to be 1 over x e to the x times a. A is whatever I have in front of my y double prime, so in this case it's 1. I can just ignore it. Now I need my Wronskian of x, or my Wronskian in terms of x. So the way that you find your Wronskian is you do a 2 by 2 matrix. We have y1, then the derivative of y1, and y2, the derivative of y2.
What did you say A was?
A is if I have anything in front of my y double prime. So that comes into play when you're doing like a Cauchy-Euler, because you throw that x squared in the denominator because you have an x squared in front of your y double prime. No problem. So we have a 1 from that A, but we need to figure out what the Wronskian is. The Wronskian we find by doing that. If you don't want to have to memorize that, you can just memorize the formula of y1, y2 prime minus y1 prime, y2. Because that's what this matrix comes out to be every time. This formula. That's what you can use for your Wronskian. It's y1 times y2 prime minus y1 prime times y2. So y1 is, here I'm solving for my Wronskian. y1 is e to the x times y2 prime. So I have to take the derivative of that. Let me take the derivatives first. We have y1 is equal to e to the x. y2 is equal to x e to the x. Derivative of y1 is just, again, e to the x. Derivative of y2, we have to do the product rule. So we do derivative of the first, which is 1 times the second, plus the first times the derivative of the second. And that's y2 prime. So now, we use this formula down here. We have the Wronskian is, that's not the Wronskian is e to the x times e to the x plus x e to the x minus e to the x times x e to the x. So if you're looking at this, I have a positive e to the x times x e to the x and a negative e to the x times x e to the x. So this term is going to go away, it's going to cancel out with that term. So my Wronskian is just going to simplify to e to the 2x. Because I have an e to the x times e to the x. And that's what I put right down here. So now this works out nicely because a lot of terms are going to cancel out. I have a 1 over x, I have an x. I have an e to the x, e to the x, e to the 2x. Those will all go away. This whole thing just becomes negative 1. So anytime you're doing variation of parameters, either your u1 prime or your u2 prime, one of them is going to cancel out very nicely. The other one will be a little bit more difficult. it won't be terrible, but one of them should simplify very easily. Or you probably messed up your Wronskian or one of your y's. But anyway, I know that this is my y1 prime, or my u1 prime, sorry. I want to figure out what u1 is, so I take the integral with respect to x. The integral of -1 is just negative x. So this is equal to u1.
What's the a in the denominator?
The a in the denominator is whatever is in front of your y double prime. So if we had like a 3 right there, we would have put a 3 in the denominator. But in this problem, since it only gave us just y double prime, it's only a 1, so we don't have it. So now we have to do the same thing with u2 prime. It's going to be positive y1, so it's e to the x times f of x over a, which is 1, times our Wronskian, which is e to the 2x. So in this case, my e to the x's are going to cancel out. I'm going to be left with 1 over x. Again, it's canceling out nicely. It doesn't cancel out as nicely as the first, but things should cancel out. So that's my u2 prime. I want to take the integral of that. I know the integral is going to be the ln of x. And the ln of x is my u2. So I now have my u1, I have my u2. I can plug those in to my answer up here, and I'll have my final form. So I'm going to... So we have our y particular is equal to u1, which is negative x, times y1, which is e to the x, plus u2, which is ln of x, times y2, which is x e to the x, and that's my particular. So now, it asks us to find the general solution, so all we have to do is add yh and yp, and we're done. This is the one question that I was talking about, where if you write yg is equal to yh plus, you just write what we did in the last question, the general is equal to your particular plus your homogeneous, you'll probably get 1, maybe 2 points off. Because in this question particularly, if you look at the solution that we got from our particular, we have an x e to the x term, and in our homogeneous we have an x e to the x term. And those are going to combine. So the way that you would combine those is we take our homogeneous, which is, so general is going to be c1 e to the x plus c2 x e to the x minus x e to the x plus ln of x x e to the x. These two terms are going to combine. So this is really going to be c2 minus 1 times x e to the x. And if I have a constant, I take away anything, I'm going to have another constant. So this, the full correct answer is yg is equal to c1 e to the x plus c3 x e to the x plus ln x times x e to the x. That is your full correct answer for this problem. The reason why it becomes C3 is because it's C2 minus 1. A constant minus 1 is a third constant. So it's C3. Does that make sense? Question?
do they want you to combine the terms and do it as like C3 plus ln of x times x e to the x, or does it really matter?
You could, that's arguably not simpler because then you have like a binomial times something. So either one would be correct. Another question?
Could we have multiplied the yp by x to avoid the common term or something?
So we only do that in undetermined coefficients because we make an assumption that our answer has one form. And if that overlaps with our homogeneous, then we multiply. That's in the beginning of the problem. In this problem, we do variation. We solve the whole thing and get this answer. We can't multiply by x because that'll change everything else that went on. So if it does overlap like that, we just account for it here. Okay? Yes. Like the plus. In this, if anybody has any questions, send me an email. Tomorrow night, 9:15 in Babio, 122. We got the nice big classroom. Thank you for coming. Thank you very much to my good friend Kevin Letty and SITTV for recording this on like 2 days' notice. I'll be sending out the link to it in a couple days when they get the video uploaded to YouTube. Any questions? Thank you for coming. Swipe if you didn't swipe.